Okay, hello everyone in a new video. In this one we are going to solve an exercise related to mechanics in the chapters of energy and linear momentum. This exercise was a previous one in the Terminal LS exams 2004 second session first exercise. The title of this exercise is Determination of the Speed of a Bullet. A gun is used to shoot bullets. Each of mass m is equal to 20 grams. Knowing that the SI unit of mass is not a grams, in order to convert from grams to kilograms, we divide by 1000. Then the mass eventually is given by 0.02 kilograms. With a horizontal velocity v0 of value v0. Now in order to determine v0, then the aim of this exercise is to determine the value of v0, which is the speed of the bullet. We consider a setup formed of a wooden block of mass capital M is given by 1 kilogram. Then here let me say that the speed of the bullet is given by 20 grams and the speed of this block is given by 1 kilograms. Now, okay, suspended from the ends of two extensible string of negligible mass and of the same length, figure 1. Then they mentioned figure now we can use it. So in this figure we can see that the bullet directed toward the block before impact or before collision. Now this setup can be taken as a block of wood suspended from the free end of a string of length L is equal to 1 meters. Then the length of the string is given by 1 meter. Initially at rest in the equilibrium position at G1. Now a bullet having the velocity v0 hits the block and is embedded in it at the level of the center of mass G of the block. So after impact, here they are telling us a bullet having the velocity v0 hits the block and is embedded in it. So when v0 hits the block, now this bullet will become embedded in the block, so in such a way that they will become one system having the total mass given by 1.02 kilograms, because the mass of the block is given by 1 kilograms, whereas the mass of the bullet is given by 0.02 kilograms. So whenever it is embedded in it, at the center of mass G of the block, then they become one system. So for this reason they are telling us just after impact the system block bullet moves with the horizontal velocity v1. The pendulum thus attains a maximum angular deviation given by alpha is equal to 37 degrees. Now G1 and G2 are respective positions of G in the equilibrium position and the highest position. So G1 is the center of gravity of the system block bullet. So, okay, when v0 hits the block, it becomes embedded in it. The position is given by G1, passing through this P level. After that, this system elevates to position at G2. For this reason, they are telling us G1 and G2 are the respective position of G in the equilibrium position and in the highest position. G1 is in the equilibrium position and G2 is in the highest position. Take the horizontal plane G1 as the gravitational potential energy reference figure 2 and neglect friction. The moment we don't have friction, the mechanical energy of a certain system is conserved, and the value of G is given by 9.8, which is the gravitational acceleration, which reflects the fact that this experiment is being performed on Earth. Now in number 1, they are telling us during collision which one of the two physical quantities, the linear momentum or the kinetic energy of the system, does not remains always conserved. So out of the following quantities we have the linear momentum and the kinetic energy. They are asking which of the two physical quantities doesn't remain always conserved, and for sure we know that this is given by the kinetic energy because always the linear momentum is conserved. And collisions are classified as elastic and inelastic depending on the value of the kinetic energy. Okay, so in this case the kinetic energy of the system does not remain always conserved. Now in number 2 they are asking us to determine the expression of the value v1 of the velocity v1 in terms of m and v0. So here we need to determine the velocity v1 in terms of these quantities. So let's recall what does each quantity represent. V0 is the speed of the bullet before impact with this block, whereas V1 is the speed of the system consisting of the block and the bullet. So since we need to determine a relation by V1 and V0, so you should always think about two quantities that are conserved, either the mechanical energy or the linear momentum. Since here we are talking about two states before and after collision, and during collision the linear momentum is conserved. Okay, so here we should think about the conservation of linear momentum. Moreover, the mechanical energy here doesn't allow us to determine this relation between V1 and V0. So let me say during collision, the linear momentum, so we need to specify the system that we are working with, the linear momentum of the system, and here the system consists of the two bodies that are colliding, given by the block and the bullet. Is conserved. Now let me write down the vector relation that dictates this condition, which is given by P initial is equal to P final. Now initially the bullet is moving and its speed carries the label 0, so this is P0, which is the linear momentum of the bullet. Now the block is not moving, it is at rest, so we will add the 0 vector. Finally, now the block and the bullet, both of them are moving together as a one system with a speed v1. For this reason here we will write linear momentum given only by p1. Okay, so here why we don't have two linear momentums, because after collision now the bullet is being embedded in the block, so they consist of one body having the same speed given by v1 and the mass is given by small m plus capital M. So now let's replace the formula of the linear momentum, which is given by mass times speed. So this p0 is for the bullet having the mass small m, so this is given by m v0, and p1 is the linear momentum of the body consisting of the bullet and the block having a mass m plus m, and with the velocity given by v1, and in this case we are interested in determining the value of v1. So what's the type of this equation? This is a vector equation. How do we solve it? Using the projection method. And here notice that we want to determine the magnitude, which is the value. So let's do projection. So here we don't have any axes, so we will project along the direction of the collision, then a projection along the direction of collision. So the direction of collision is from left to right, so this is the positive direction. Now we'll drop all the vector quantities, and each vector quantity will carry a plus or minus sign. No need to worry about the cosine because everything is collinear. So notice that v0 is pointing in the positive direction of the collision, so this is plus m v0, which is equal to, now because we want to determine v1, so no need to project v1. If v1 is positive, then it will be in the positive direction. It's negative, will be in the negative direction. Moreover, we want to determine the expression. In this case, this is given by m plus m. Here we have v1, and we are interested in determining v1. So if we rearrange for v1, then v1 in this case is given by small m, which is the mass of the bullet, divided by the mass of the body consisting of the bullet and the block, multiplied by the initial velocity of the bullet. So here let me write that v1 is equal to m divided by m plus m multiplied by v0. So as you can notice that the connection between v0 and v1 is done using the linear momentum. Okay, now number 3, part A, they are telling us part A, determine just after the impact the mechanical energy of the system pendulum earth in terms of v0, m and m. So here the pendulum, here we are referring to the pendulum which consists of the bullet and the body together. Okay, so this is just after impact, because now the block contains in it the bullet. So they are telling us just after the impact, the mechanical energy of the system in terms of V0 m and m. So let me make some space. We know that the mechanical energy of the system is given by the kinetic and the potential. Now here the system consists of the block and the bullet together. So we want to determine this mechanical energy in terms of V0 m and m just after the impact. So just after the impact, this system is at the point G1. So for this reason, this will carry the label 1. This is 1, this is 1. So I repeat, just after the impact, whenever V0 collide with this block, just after the impact, this body is being at the position G1, so yet it didn't elevate. For this reason, we are determining the value of the mechanical energy at the point 1, and luckily in this case, we can say that PE1 is equal to 0, and the reason is given by passing through the PE level. So this is 0. Now what about the kinetic energy? Is quadratic in speed, and just after the impact, the speed of the system is given by V1, so this is V1 square. Now what about the mass? Recall, it's not small m or capital M, but rather the sum of the masses, because it consists of two parts, the bullet and the block. So this is indeed the expression of the mechanical energy in terms of V0 m and m. Now in part B, they are telling us determine in terms of capital M, G, L and alpha the mechanical energy of the system pendulum earth at the point G2. So we need to determine the mechanical energy at the point 2. So mechanical energy at the point 2 is given by kinetic and potential. And now here, because they are telling us just after the impact the system moves with the horizontal velocity v1, the pendulum thus attains a maximum angular deviation. So this is the maximum position after the impact. So in this case, the system stops at the point 2. So whenever it stops at the point 2, it means that its speed is 0. And here we can deduce that the kinetic energy at the point 2 is given by 0. The system stops. Or we can say maximum height. So in this case, this is just equal to the potential energy at the point 2, which is given by the mass multiplied by G multiplied by the height. And in this case, the mass that we are working with is given by small m plus capital M multiplied by G multiplied by H2, which is this distance, which is the distance from the center of gravity G2 to the PE level. Now notice that here we want to determine this expression in terms of M, G, L and alpha. So far what we have done is in terms of small m capital M, G, whereas H2 must be converted into L and alpha, and this can be done from the geometry of the figure. Now notice that here, so we are interested in determining this height. So let me include this as a part of the answer. So this is G2. This is the string. This is alpha. We are interested in determining this height, which is H2, measured with respect to this PE level. So this is the PE level. So when the pendulum is in the equilibrium position, it passes through this point. So if this is L, then this will be L. Now we are interested in determining H2. So H2 in this case is equal to what? Then here let me label some points. If this is A and this is B and this is C, so H2 in this case is this distance from G2 to the PE level, which is AB, and AB in this case is nothing but AC from A to C minus BC. Okay, so AB is nothing but AC minus BC. Why so? Because we know that AC is equal to AB plus BC, so AB is nothing but AC minus BC. So this length here is the total length minus the length from B to C. Then in this case, AC from A to C, when G2 is in the equilibrium position, G2 coincides with A, we can notice that the distance from C to A is nothing but the length of the pendulum, which is L. What about BC? BC can be related to the angle alpha via the cosine, because BC with respect to alpha, it is an adjacent. So if you complete, this is the right triangle, this is the right angle, and this triangle, this is the hypotenuse, and we can notice that BC with respect to alpha, it's a cosine. So in this case, cosine alpha is equal to BC divided by, this is L. Then if we rearrange for BC, then BC is given by L into cosine alpha, so minus L into cosine alpha. So taking L as a common factor, it would be 1 minus cosine alpha. Now replacing the expression of H2 here, we can notice that the mechanical energy at the point 2 is simply given by the mass, which is given by M plus capital M multiplied by G multiplied by L into 1 minus cosine alpha. And how do we know that if our expression is correct? Notice that if G2 coincides with the point A, then the value of the mechanical energy would, the value of the potential energy would be 0, because it's passing through the PE level. And in this case, if G2 is at the point A, then the value of alpha is 0. So let me repeat this. So how do you know that our expression is correct? Now if G2 coincides with A, then alpha would be 0. If we replace alpha by 0, then this would be 1 minus 1, because cosine of 0 is 1. So 1 minus 1 is 0. So this will be 0, which reflects the fact that if G2 is at the point A, the value of the potential energy is 0. So and in this case, we can say that the mechanical energy at the point 2 is given by M plus capital M multiplied by G L into 1 minus cosine alpha. Now in part C, they are telling us to deduce the value of V0, and by deduce it means that we notice the previous parts. In the previous parts, we have determined the mechanical energy of the system block bullet at 2 different instants given by 1 and 2. So here we need to deduce the value of V0 by just simply using the conservation of energy. So here let me say, since there is no friction, and this is being mentioned in the text, then the mechanical energy of the system, and this system consists of, for sure, the block, bullet, and we don't forget the earth, because it's the one which is causing gravity. For this reason, we have gravitational potential energy. So in this case, we know that the mechanical energy at the 2 instants, they are equal to each other. And here on the left, I will place the mechanical energy that includes V0, and it's given by 1, and this is 2. So mechanical energy 1 is given by half M plus capital M V1 square, which is equal to mechanical energy at the point 2, which is given by this G into L into 1 minus cosine alpha. And in this case, we are finding the value of V1 square. So what's the type of this equation? So this is given by, okay, so here we want to determine the value of V0, but in this equation we have the value of V1. But moreover, we have a relation between V1 and V0, so after determining the value of V1, we can deduce again the value of V0, okay? So what's the type of this equation? This is quadratic in V1. So this simplifies out with this, and this reflects the fact that the mass doesn't play any role. So in this case, V1 square would be equal to, so here half, taking it to the right hand side, it will be a 2. So 2g into L into 1 minus cosine alpha. So now plugging this on the calculator, then the value of V1 square would be given by 3.95. So let me place the values. So 2 multiplied by 9.8 multiplied by the length of the pendulum, which is given by 1, multiplied by 1 minus cosine 37, because alpha, the value of alpha is given by 37. And here we need to make sure that the calculator is in the degrees mode. Now plugging this on the calculator, then the value of V1 is given by 3.95. Now in this case, V1 would be the square root of 3.95, which is equal to almost 2. Now because everything is expressed in the SI, so the speed of V1 would be given by meters per second. Now notice that here I didn't place any unit for V1 square, because it's not V1, it's V to the power 2. So here if you want to place a unit, it must be meters square per second square. But in the question they are asking us to determine V0. Now V1 and V0 are related via this equation. So let me write V1 is equal to m divided by capital M plus m multiplied by V0. And we are searching for the value of V0, which is the speed of the bullet, which is the aim of this exercise. Now if we rearrange for the following equation, we get that capital M plus m divided by small m multiplied by V1 is equal to, so capital M is given by 1 kilograms, whereas the small m is given by 0.02 divided by 0.02 multiplied by the speed of the system, which is given by 2. Now plugging this on the calculator, the speed is given by 102, because everything is expressed in the SI, so the value of V0 will be given in the SI, which is meter per second, and this is the order of magnitude of the speed of a bullet. Remember that the speed of a bullet is very high. So 102 multiplied by 3.6 can reflect the speed of the bullet, which is above 300 kilometers per hour. Now in number 4, they are telling us to verify the answer of question 1, and in question 1, we have mentioned that the kinetic energy of the system is not conserved. So let's calculate kinetic energy final and kinetic energy initial, and we are talking about the kinetic energy before and after the impact. So initially, we have the kinetic energy of the bullet plus 0, because the block was not moving, which is given by half mv0 square, which is given by half. V0 is given by 100, sorry, the small m is given by 0.02, and V0 is given by 102 to the power 2. Now plugging this on the calculator, its value is given by 104.04. Everything is expressed in the SI, so this is joules. Finally, kinetic energy final, this is given by, so finally it consists of a one system, which is given by kinetic energy 1, which is equal to half the total mass multiplied by the speed 1 raised to the power 2, which is half 0.02 plus 1 multiplied by 2 to the power 2. Plugging this on the calculator, then the kinetic energy is given by 200 for everything in the SI, so this is joules. Now let me state that since kinetic energy initial is different than kinetic energy final, one of them is 100, around 100, and the other is around 200. For this reason, then the kinetic energy is not conserved. And if you want to classify this collision, it would be inelastic. Then the kinetic energy of the system, here we are talking about the system which is given by block, bullet, is not conserved. So that's it for me in this video, guys. See you soon in a new one.